So hello everyone, welcome to the shelter, heating, cooling, and lighting track. Today our goal is to demonstrate how advancement in power, shelter, and data-driven modeling approaches support community and infrastructure resilience in face of natural or man-made disasters. We have 3 main sessions. We'll start off with our 2 invited speakers. Our first speaker is Dr. Jonathan Gourley from NOAA National Severe Storm Laboratory. He's also an affiliate associate professor with the School of Meteorology and Civil Engineering Department at the University of Oklahoma. Our second invited speaker is Mr. Scott Clark, Director of George Washington University Solar Institute and President of the Stella Group. We will have a short Q&A after each presentation. Please feel free to ask your question in the chat box and NOAA webpage or the Zoom chat box you see at the bottom. The second part is the panel discussion. Our panelists are Dr. Bandona Carr from Oak Ridge National Lab, Dr. Jess Thornburg from Grapefruit, and Mr. Scott Clark. We will conclude our session with 2 presentations from Decadome and Grapefruit, which show us examples in real-world situations. So without further ado, I would like to invite Jonathan to kick off today's session. Thank you.
Okay, I've unmuted myself. Hopefully you can hear me okay. Seeing a nod there from Shima. So thank you for the opportunity to speak today. So I'm coming from the National Severe Storms Laboratory, or actually in my basement, like many of you. And I'm going to speak today about post-wildfire hydrometeorological observations and forecasts. So I should be sharing or showing my presentation. It's taking my computer a moment. So there it appears on my end. Very good. Okay, so just to begin with, unless you've haven't watched any news whatsoever, then you're probably aware that we've had just a heck of a wildfire season in the Intermountain West. So many states have set records for duration and intensity and size of wildfires. So in fact, I think in Colorado right now, we have the largest wildfire in state history is presently underway. Just to give a little more background on myself, this is where I'm coming from. So this is a National Weather Center, normally where I would be in this building, and we house a number of entities, a lot from NOAA. So these are listed here. The National Severe Storms Lab employs the most personnel in the building. And then we have state agencies like the Oklahoma Climatological Survey. We also have a large state presence with the University of Oklahoma. We're on the campus of OU. So we have the School of Meteorology that's up on the 5th floor. And then the College of Atmospheric and Geographic Sciences is also located in the building. So this kind of shows you, you know, some scenes that you might see in the spring. You know, we're kind of famous for tornadoes and chasing and doing that kind of research. Also, a little known fact that our laboratory was involved in the early days of doing the research and development and ultimately the application of what's called the NEXRAD radar network for the National Weather Service. So that's what's shown here, and that's really the bread and butter of a lot of the research that underlies our research. So I'm going to switch to Colorado. So this is in southeastern Colorado. That you can see here, and then this was a burn area here. So what's shown in the kind of reddish and orange colors are the burn severity index, and so this whole area experienced a wildfire, and then as a result, I've been involved in setting up an observation network there, along with a number of partners, including the Colorado Department of Transportation, United States Geological Survey, State of Colorado. So there are a number of collaborators who are involved in this work. And one of the biggest concerns here for those that aren't aware of this is that after there's been a wildfire, what happens A lot of the vegetation is removed. Also, the soils can actually seal up and they can act what we call hydrophobic, in a hydrophobic way. And so that means that you don't have the ability for the vegetation to hold the soils in place. And so you have more sediments that are being displaced that can cause a debris flow. Also, the infiltration rates are reduced. So you don't have as much absorption by the soils of the rainfall. And so what can happen after a burn like this, and this is what certainly we're going to hear about come this winter and through the next few years, are debris flows and flash floods on these burn areas. In this particular situation, there's a little town that lies down here called La Vida, which is a nice little touristy town. So people like myself that live in the kind of flat, hot areas in Oklahoma and Texas, we kind of try to migrate there to the west, where it's a little bit higher elevation and cooler and prettier during the summertime. So it's a tourist area. The issue is, as you can see, a lot of these streams that are emanating from the burn scar all converge here in this little town of La Vida. So most of the people there are transient, they're not permanent residents. A lot of them are completely unaware that the area up there in the mountains have been burned and that they're in a risky area. So that's the concern. You can see here that we have a number of instruments that have been deployed in the burn scar and then immediately downstream from it. So we have 11 surface velocity radars, and I'll show a few more details about what these are actually doing. A number of rain gauges. We have stage radars, so they can see how much water is in the stream, soil moisture sensors. And then this was the one I was mostly involved in, which is an Xband polarimetric radar. So this is a mobile weather radar that we move here is where it's shown, and then we can scan the whole area. So this is a few more details about the mobile Xband radar. So this is a picture of it that's shown here. So you can see it's fully mobile. You might have seen, if you've seen some like OETA specials and things like that on NOAA, that these are used to do a lot of tracking of supercells, tornadoes, that kind of thing. But during the summertime, then this is a time when we don't have as many tornadoes, and folks like myself have access to the instrument, and then we can do things on a more of a fixed basin deployment. And that's what we're doing here. We're not moving it around. We simply drive it out there, park it, and then we scan the weather whenever it occurs. So these are some more details I won't go into, but what it does is it provides you full surveillance of the atmosphere around there, with a particular emphasis over the burn area. Another instrument suite that I was involved in were these stream radars. And so this shows one here. It's a kind of a unique instrument in that it actually has two radars. So one of them is pointing straight down. And so whenever the stream is rising, then it can measure that distance from the radar to the stream. And if that distance decreases, then you can determine that you have an increase in the river stage. Also, you have this other radar that's pointing off angle, like either upstream or downstream. And so this is using the same principle as whenever a police is tracking your speed in your vehicle. It's the same principle here. In this case, it's looking at tiny little ripples on the surface, and those have a velocity that's often the same as the water moving upstream or downstream. So from that, we can get a surface velocity and see how quickly the streams are responding. So these are very useful instruments. Notice that this one is attached to cableways, so we can put them on cableways and any kind of infrastructure. Okay, so this whole stream radar project was part of a bigger NOAA funded project that I led that we called Anchor. So Automated Non-Contact Hydrologic Observations on Rivers, or Anchor. So we had 14 commercially available units that we demonstrated. And so this shows you across the United States several of them that we installed, many on railroad bridges, like is shown here in the bottom right. All of these are actually railroad bridges. And so this took a little bit of work on my side to develop an agreement with Union Pacific. So they gave us permission to install them on any of their bridges. And they've got many bridges throughout the whole central and western parts of the United States. So so that it took some coordination with them to, you know, to get somebody employed by UP, Union Pacific there to make sure trains weren't moving whenever we did the installation. We also installed on a number of box culverts, and I'll show those in the next slide. And so really we had a number of objectives in the study, everything from water resources management. Each side had a different emphasis. Debris flow monitoring, assimilation, and really flash flood monitoring were the major goals. So this shows some of the different deployments that we had. So this one was in Cherry Creek, Colorado, and really in Denver. So this was an urbanized area. This was co-located with a number of other sensors using both visible methods for retrieving surface velocity and then also conventional sensors by the USGS. So we did some for merely intercomparison purposes. This is also co-located with a USGS sensor in Oklahoma. And then this was a sensor that we placed above a church camp. And I'll show some data from this one in just a moment. And so this one was attached by, this is a water treatment facility, and then the other cableways are attached to trees. And then lastly, this one was placed in San Marcos, Texas, where they have more of a concern for low flows and maintaining spring flows for some endangered species there. So this is on a box culvert, much easier to install this one. And you can see this is the entire infrastructure, pretty light, solar panel, uses cell communication. That's it. We could go out there and install 2 of these in one day and be done with it. By the end of the day, you're getting measurements, which is pretty nice. So this shows the sensor that we installed on Falls Creek. So this has had some extreme flash flood events in the past. And what's happened in the past is they had a big flash flood, and this nice little calm, gentle stream that runs through their camp turns into a raging torrent whenever they get heavy rainfall. And it's done this in the past, and it's isolated campers so that they basically created an island there, and they couldn't get to them for about 36 hours at one point. And so downstream of this, during normal times in the summertime, they'll have as many as 7,500 campers that are there. And so what we did is we installed the sensor upstream, and then within 2 months, we had this event occur, which was truly amazing. If you look, this is what the stream normally looks like. And then if you look at the trace here on the water level, it went from basically nothing to 10 feet. So it came up over our sensor, which was a little bit unexpected to say the least. And it did so in 1 hour. You know, the water went from here to covering the sensor in 1 hour. And so we had some damage that occurred to the sensor, but it survived it, believe it or not, and provided measurements even after that, after the abuse it took. So the radars inside are actually encased and waterproof. And so what happened here was debris hit the cables and ripped it apart. So it was this housing that was sacrificed. Also, something else that we saw that was interesting is that the velocity increased 1 hour prior to the stream actually rising. And so we saw that quite a few times with the vents on this, generally in areas that tended to be a little bit flatter, had this kind of a response where you saw the velocity leading the stage. Okay, so now going back to our basin out in southeast Colorado. So this is showing the number of rain gauges that we had placed out there. And this is the whole season time series, by the way. And so what I did is I showed this particular event that occurred in the summer of 2019. And so these are, you know, 1.5 inches, 1.7, 1.6. And so this is this event right here. So you can see it's pretty widespread across the basin. From my perspective, and I don't know where the audience, where you're from, if you have 1 to 2 inches is really, this is almost a beneficial rainfall amount. I mean, this is not a problem, at least by standards in the Southern Plains or Southeast, not a big deal. But over a burn area, this can be extreme. This can cause flash floods, as I'll show in just a moment. That's enough to do it. So what this is showing is the animation, I hope, of the radar data from the nearby NEXRAD radar. So it provides wide area surveillance, whereas the radar that I was operating was right here, much closer to this basin. So much higher resolution than what we're going to see here. And then also, this is the log that's shown on the, hopefully you can see that on the upper right, that I was taking. So you can see there's a storm that kind of moved up on the northern end of the burn area, and it's producing heavy rain. And then it's starting to drop south over the burn area. And then you can see I'm looking at the Doppler velocity. I'm saying I'm getting 50 knots inbound. So that's about 50 miles an hour. That's blowing towards me. So that's quite a bit. And then you see a couple of other observations that it's moved to the east. I even got some small hail where I was. So any case, an interesting event. Also note, this was the first day I arrived, we had a little storm and I just went up and tested the radar and kind of exercised it. This was day number 2. So this was the first day we were actually operational and we got this event. So we really got there just in time for this event, the biggest one of this season. So this shows some of the pictures of me operating the radar, and this is the burn area that's shown back here. It's kind of to the west of this. These are the Spanish Peaks, and their burn areas back in this region. And then this is the picture that I took during the event. And I, not having had experience with this particular area, I've been in mountains plenty of times, and you get afternoon thunderstorms, not a big deal. So I was like, gosh, is this anomalous or is this the big event? And you can tell just by looking at that, with my experience looking at thunderstorms, I'm like, this looks pretty scary, and sure enough, it was. So this shows some of the imagery. I won't go into the gory details of what this is, but these are the data that I collected with the mobile radar data that I showed just a moment ago. So you can see the storms are pretty well on top of me at this point. This is a velocity, so you can see there's air. This green arrow means that the wind is blowing towards me. Usually when that occurs, that's an indicator that the storm is gusting out. It's on its way to dying. But what's unique about this, you can see the red arrow that's still feeding in. So you still had this feed of air going up into the thunderstorm, and that's what's providing the heat, the moisture, the lift that keeps the thing alive.
So Jonathan, one more minute.
To the end now, I'm showing the time series here that you can see. This is showing the precipitation and then the surface velocity. So this is showing precipitation from the rain gauge, and then the surface velocity from one of the stream radars that was on Indian Peak. And you'll notice that the difference in these peaks is only 4 minutes. So that's indicating to us that as soon as that rainfall is hitting the ground, it's basically going right in the stream and causing a response. So you're really not getting a whole lot of time if you've got these kind of in situ sensors that are placed. You need to be looking at data as the storms approach this, that the storms are simply responding. I mean, the streams are responding very, very quickly to the rainfall. So this shows the aftermath of what occurred here. So we did have a lot of mobilization of debris, getting up to boulders. So you can see a lot of movement of mass in the area. So this it surprised me. I mean, only an inch and a half of rain, and you get this kind of a surface response was an eye opener for me. Go right to my findings here is that our present day operational observing networks are really insufficient to deal with flash floods and landslides, debris flows that are emanating from burn areas. So our initial insights that we have found is there were some meteorological clues that indicated we were going to get some heavy rainfall. The stream responds very, very quickly within the causative rainfall. So it's best to be monitoring the radar data prior to it landing on the burn area. Surface velocity tends to be more reactive than the stage increases. So you see the surface velocity respond very quickly. I didn't show or didn't concentrate on the soil moisture, but it shows almost no impact. Didn't respond to rainfall hardly at all. So the idea of thinking that there are antecedent soil moisture conditions causing higher hydrologic responses doesn't really apply on burn areas. So the next phase is we're going to actually use the radar data that I showed there to estimate the rainfall rates, and then we can start resolving the variability of rainfall, very high resolution. And then we're going to continue this into next season. So with that, I'll go ahead and stop and hand it over to Shima. Hopefully I didn't go too far over time.
Thank you. Thank you for that great presentation. Is there any question from the audience?